In this video, we'll be talking about the second order integrated rate law. So the rate laws we've looked at so far are differential rate laws. So a second order differential rate law might look something like rate equals K concentration of A squared for a reaction of A goes to B plus C. This would be something that is overall second order, but also second order with respect to a single reactant. Our second order integrated rate law is going to look like 1 over the concentration of A, and this is the concentration after some amount of time that the reaction has been proceeding, minus 1 over the initial concentration, usually denoted with a subscripted 0, of A, equals K, which is our rate constant, times the amount of time that the reaction has been occurring. And this comes from calculus. We don't need to know for this class how to get from the differential rate law to the integrated rate law. And we can rearrange our integrated rate law a little bit by adding 1 over the initial concentration to both sides of the equation so that we get 1 over the concentration of A at some time equals our rate constant times time plus 1 over our initial concentration of A. But why would we want to do this? Why have multiple forms of our rate laws? Doesn't that just complicate our lives? Well, if we're in the lab and we're measuring a reaction in real time as it's occurring, like you've been doing in your Chem 132 lab, if we were to graph 1 over the concentration of a reactant as a function of time, and we were to see a straight line, right, a linear relationship, that would actually correspond to this equation that we've written above, where 1 over the concentration of A is our y value, t is our x value, or our independent variable, the slope would be k, our rate constant, and the y-intercept would be 1 over our initial concentration of reactant A.